Thank you, Dave. Afternoon, ladies and gentlemen. So my name is Nathan Rittenhouse, and I'm going to be talking about symbolic fuzzing, or problems that you can run into when you actually employ these kind of techniques. So who am I? Well, I'm just some dude who got a bachelor's and master's degree from a technical college in South Cambridge, Massachusetts. That's all I need to say about, all I can say about that. And right now, I have my first, I guess you could call it, real job at a startup in the Bay Area called Area 1 Security. And this is mostly focused on the work that I did during my academic years, not really anything that I'm currently working on. So to start off, we need to explore what exactly these symbolic techniques are going to do for you. They can help you uncover a lot of different bugs in a program that might be very tedious to uncover if you weren't using symbolic assistance. So you might be able to uncover integer overflow bugs, array dereference bugs, or character control character induced bugs, such as, well, for example, making a stir copy take in a string that's too large for its buffer. So what you can also do, which is more generically important to both attackers and defenders, is it can help you find bugs to vulnerable code blocks inside of your program. So with that, because of the fact that this technique can be employed in a lot of areas where we do a very in-depth modeling of a program's control flow, there are a lot of techniques that have been built either in conjunction with this or on top of it. So we're not going to cover how to discover race conditions or dealing with a bunch of kernel user mode changing programs or stateful network protocols or automatic exploit generation, which is it's a fun topic. Lets you know whether or not you actually can take a bug that you managed to cause a problem in a program with and make it into an exploit. It's a great topic, but we're not going to be covering it. Also not covered in this talk are browser object-related vulnerabilities, all the use after free kind of vulnerabilities that you see in Internet Explorer, Firefox, or Chrome. We're not really going to be looking at that type of bug. There's plenty to look at in this area without focusing on those. Also, determining whether a test triggers a bug, I can go over that a little bit, but it's not going to be a big focus of the talk because there are a lot of ready-made tools such as Valgrind, and pretty much any debugger that you could hope to use will give you a good idea of whether the bug that you triggered was triggered in such a way that there was a problem in the program. So another thing that we're not going to talk about is grappling with obfuscation or anti-debugging. We're going to assume that the programs don't have so these techniques can deal with obfuscation, a lot of forms of obfuscation very well. However, we're not really going to focus on that. We're not going to focus on that. So when I say all this, I've told you what we're not going to talk about, and a little bit of a high-level view of the talk, but here I'm going to get to the meat of what we're really talking about here, the technique that we're going to focus on, or at least what this technique gives you, the tester, to use to test the program. You'll get what's called a path constraint. And a path constraint is a sequence of, you could call them a formulae that you have to satisfy in order to reach a code block that might have a bug in it. The other part of this often very large formula. We're talking multiple gigabytes, thousands or millions of clauses, thousands of variables. Formula is what's called a bug query. And this is a formula that if you satisfy it, and you are able to satisfy the path constraint to reach that vulnerable code block, will yield you an input that will trigger the bug. And hopefully in a way that you will actually notice whether the program actually was vulnerable to your input or not. You didn't just have a fluke. So what separates this technique? Why do we need this path constraint? Why do we need this bug query? The reason is that if you do random mutational fuzzing, for example, you could even generalize what I'm saying here to fuzzers that have knowledge of your file format. And for example, a lot of Peach's default mutators this would apply to, where you're saying, well, for this part of the file, I'm just going to, without any knowledge of what the program is doing, write a value there, or write values to multiple parts of the file, and try feeding it to the program. You will often generate a lot of test cases that don't actually reach very far into the program. You'll often hit error checking logic that says, hey, your input's not valid. We're not going to process this, and we'll just exit and you get nothing. Symbolic execution can guide you around those checks. So what we're really going to focus in this talk, and I know I've said this statement a lot, but there's a lot that happens in symbolic execution. I'm going to explain at a high level the process that almost any tool that you'll find out on the web today will use in order to test a program through this method. We're going to focus on path exploration strategies. So remember when I talked about a path constraint? Well, what I'm going to talk about here is how we get those path constraints. What is the method for enumerating the paths that we're going to check for bugs in the program? And in some cases, how to make a path constraint that might not have let you trigger the bug actually let you trigger the bug. So related to getting these lists of formulae, which is really what you're doing with it. There are also optimizations to speed this process up that you can perform on the individual constraints themselves. Some of them will be mentioned, but they will not be the focus of the talk. So out of all the past infiltrates or all the past conferences, why would it be relevant for me to give this talk now? The reason is that there is a ton of constraint generation code available. There is a ton of symbolic fuzzing code available now. So I have a decent list of some of the frameworks out there, but it's by no means exhaustive. The other thing that actually gave rise to these tools was the creation of solvers that were actually able to solve these path constraints and bug queries in a reasonable amount of time. Because remember what I had said before was that these constraint lists can grow to millions of clauses and thousands of variables. So you have to know what you're doing if you're going to solve them quick. Not you, the user, but you, the solver writer. So those are some of the new ones. And one of the reasons you might want to know about this is because of the fact that there are so many of these utilities available. You might have to either make one work for an application that was breaking under it, or for whatever reason, maybe it's because of your job or maybe because you want to, you might need to repurpose one of these to work on a program that it didn't. Or implement a new strategy that uses a combination of the techniques I'm going to talk about. So what does symbolic fuzzing look like? Well, most people think that we basically have this thing called a symbolic executor in a target program, and they're kind of these very separate things. Well, they're kind of not. So you're going to run your program inside of a symbolic executor. And what is this symbolic executor going to do for you? It's going to generate the constraints, namely the path constraint and the bug query. It's going to process them in some way, and the processing stuff is what we're going to focus on in this talk. And then it will solve these constraints, get you a new input out, and then see whether that input is actually able to cause a problem in the program. And so here's an example of some of the, so you can fuzz all of these different formats using such a technique. But fuzzing is still fuzzing, and at the end of the day, you want that thing to blow up. Now, these are just 3 boxes that are kind of conjoined in a loop, but there's a lot of complexity here. A lot of complexity that will limit the number of test cases that you can generate and send to a program, and thus you are also limited by how much of the program you can test, and well, how many bugs or if you're gonna go through and write an exploit, or how many exploits you can write. So the first step is constraint generation. We need to generate the path constraint so we can generate the bug query. That involves taint analysis, because we need to know, and yes, I know that some people have said this is a very funny phrase, all right, but that's the real word. That is the real phrase for this. I've just had too many people ask me, is that the actual term? It is. So in order to do this, what you in effect have to do is rewrite the program in real time somehow, or run it inside of an emulator, so that instead of executing the instruction as you normally would, you're going to execute a modified version of the instruction that actually gives you a constraint and actually executes the instruction so you can keep running the program. This has a lot of instructions, often in order of magnitude more instructions than what you had before. So that can slow your program down. Now, in constraint processing, you'll need to do a lot of fix-ups on the formula that you have in order to either create the bug query properly, or make it actually perform well on the solver. And another goal that you might have if you're trying to audit a program is you might want to make the constraints a bit more readable by a human than they would have been if you didn't have this goal. So you might have to maintain a lot of state for this. And remember, these formulae are large, so even a linear pass over your formula it could take a significant amount of time. You also may need to partially evaluate constraints, as in actually execute code to say, okay, I'm going to perform this operation as a CPU might perform it in order to get a smaller formula so that it evaluates more quickly in your solver. In terms of solving this formula, it's not an easy problem. It's actually an NP-complete problem, which in more or less words means that in a way that's relevant to us, it means that the best algorithm that we know to solve a formula like this takes time exponential in the number of variables that we have. And that's also related to how big the variables are too. So remember, we're talking about thousands of variables, and often they grow to 64 bits or more in size. So in the worst case, this could take very, very, very long. And if, for example, you're dealing with cryptographic code, you might not be able to solve the formula. And we'll get around how you might deal with a program that does have these kinds of clauses inside of it. So next I'm going to cover path selection strategies. So before I do that, I want to get some of the terminology, or just some of the markup, if you will, down so that you can more effectively read the code that I'm going to put for the test applications, or the applications that we're trying to test So green variables are tainted data. What that means is they are values directly read from your program input. Tan variables are pointers to tainted data. So what that means is, for example, they are pointers. It could be a pointer to the beginning of an HTTP request that you made. So constants, the ones that are important, the ones that you should pay attention to, are in light blue. So those are pretty much just going to be numbers, maybe, yeah, just numbers. So now let's get into the types of path selection strategies that we can look at, or that are really available to us now. So we have pure symbolic execution, which tries to exercise every part of a program. We have pure compilic execution, which is a bit more capable of reaching bugs deep within a program. And what we then have are some enhancements on concolic execution, which are called generational search is one of them. And goal-directed branch enforcement, which is actually a technique that I worked on with my former lab at that college in South Cambridge. On top of this, there are also some enhancement strategies. I'll just start going through the path selection strategies and not spend too much time just reading off like a list of things. So what is pure symbolic execution? This approach to testing a program is basically exercise every path that you possibly can within the program. And if you've exercised every path you possibly can in the program, you will know whether or not there are bugs in it, assuming that the program is deterministic and some other, well, mainly that assumption. So there are some not so obvious problems that you have to deal with this, aside from the fact that it's kind of slow because you're often running the program in an emulator. But the most obvious problem is what's called state explosion. So say that we have a program that just reads in two tainted variables, I and j. Right. So I is equal to 3. If I is equal to 3, we're going to say you got it. If I plus j is equal to 31337, it's a very loved number around in this part of the community, we're going to say God mode on, because everyone remembers IDDQD, IDKFA from Quake, right? No? No. Oh well. So here's what performing symbolic execution is going to look like. We can have an input that makes that when we run this program through the symbolic executor, we'll see, oh, we're going to check if I is equal to 3. All right, well, now we need to generate an input that tries to make I is equal to 3 false, which could be I is equal to 4. Or we could set it equal to 3 to make the branch flip to 2. So we can do that, and then from there we can go different directions on I plus j. So we can either have I plus j equal to 31337 or I plus j not equal to that. So what you can see here is at the last level of our branch tree, we have 4 different inputs that we could use to exercise every path in the program in a different order. So the number of constraints that we have is 2. Well, if you keep cranking up the number of constraints, well, if you have 3 of them, you're going to have 8, right? You're going to have 8 inputs and so on. So this process is going to take you'll have an exponential number of paths that you have to exercise. And remember, every one of those steps is going to take a lot of time. So some people think, oh, well, computers are fast. Like, so what? We have these, we have like multi-core and all this, good stuff, and that's all. Modern computers should be able to mulch through a problem like this. Well, not so fast, because here's an example from a very well-known paper on pure symbolic execution. It's for a tool called Cleat. Highly recommend you look at it. The program with the maximum number of of states reached was GNU host ID. And remember, this is a GNU utility, so this is not exactly MathCAD, for example. Like it's not, or imagine whatever program you want that's extremely complex. Of course, they have a lot of error handling logic in there that a lot of other programs don't, but that's beside the point. What it does conceptually is kind of simple. So we have about 100,000 concurrent states reached at once. So each of those states is basically equal to one of the junctions between an arrow and the two arrows below it here. So it can look at about 100. It looked at 100K of those at once using 1 GB of memory. Well, so let's do some simple math here and see what happens when we increase the branch depth to 18 as opposed to 17. Well, if you want to go to get 18 branches deep, you're going to have to take 2 GB of memory. And 19, well, you're going to have to double again. So that's 4 GB of memory that you'll need. So if you want to look at all paths at depth 30, you'll need nearly 1 TB of memory. And, well, again, you'll have this exponential doubling factor, which is going to make this problem intractable very fast. And what evidence do I have for saying that? Well, here are some statistics from other papers that use a different approach called concolic execution. So in the paper that I worked on with my former MIT team, the minimum branch depth that we reached for any of our bugs was 35 branches deep in the program. This is way over 1 TB of memory that you need to reach a bug like this if you tried to find the bug with pure symbolic execution. Sage, which actually pioneered a technique which is called generational search, which is layered on top of what's called pure concolic execution, managed to find about a mean depth of way over 30 for the programs that it was finding bugs in. So, by the way, I should probably note that the reason that all of these applications are labeled so generically is because this was out of Microsoft research, and they're not going to want to tell you what programs they found bugs in, because, well, it could make them, you can imagine the political reasons that a company like that might not want to tell you where the bugs are. Let's see. So we want, just to recap, we want a different approach that will let us exercise bugs that are very deep within a program. So the idea of this approach, and what the pure approach is to doing this, is you take a sample input, you feed it to the program, and you look at the list of conditions that were met by the program, and what potentially vulnerable code sites were reached during the program's execution with that input. So what you can do is take a look at this list, and you'll have a path constraint to reach a vulnerable code site and a bug query to hopefully trigger a vulnerability at that code site. So what do we think? Well, we found a path to a bug. Oh, awesome! That means we are going to have an O-Day coming out of the solver in a few minutes, and we're going to be able to complete our pen test or sell it to another company for buku dollars and win pwn to own, and without any manual labor. Well, unfortunately, that's not always the case, and often not the case. The reason is because programs are a little bit more complicated than people think they are. So we're going to take an example that is, as you might have heard of in CSI, it's a composite of behavior I've seen other programs elicit. And we're going to take a look at this fictional code block and take a look at how a pure concolic execution system would deal with it. So what this program does is it reads an input I, reads an input J, does some safety checks on them, namely it makes sure whether that they are less than 1 million in value each. It might do some others. It basically doesn't really do anything else, but other programs like it do. And then it will perform a malloc operation that is vulnerable to an integer overflow. So what our goal is to make this integer overflow on zero buff equals I times j be smaller than the number of bytes written into it in the following two nested loops. So when we read input I and input j, that's not just simply a variable declaration. You actually have to do an Indian swap to make that happen for a lot of file formats, because depending on what byte order your processor uses, if it doesn't match up in the file format, it would match up with the one used in the file format, you'll have to reverse the byte order to get the intended value for that variable. Second, the sanity checks are pretty simple inequalities. But we also have to do type fix-ups, because in order for us to query for this bug, we're going to need to use 64-bit variables and not 32-bit variables. Because in the case of the solver that we're going to use, called Z3, it's written by Microsoft Research and has recently become pretty open source. I'm not going to say it's actually open source, but it's pretty close. You can't check whether a number is greater than, or a quantity is greater than the bit width of its operands, and all of the operands have to be of the same bit width. So we have to promote the bit width in order for us to check whether it's greater than the largest value that you can put into a value of the bit width that the program actually uses. So we generate those type fix-up constraints and generate the bug query as well. So what does this actually look like in Z3? I can just go through this kind of quickly. So those are the type fix-ups. We have the Indian swap for J after it's been read out of the file and had its byte order reversed, so it's actually readable. And the same thing for J. And the formula, well, we have this bug query that says the quantity of the Indian swapped I and the Indian of the product of the Indian swapped I and Indian swapped J is greater than the largest 32-bit integer. So what we think we'll see is an input that looks like this generated by Z3, and we're going to have our O-day. Unfortunately, that kind of program is not what we'll actually see. What a real program would do is, well, so this is one case. I can't say all programs do this because all programs are different. But one technique that I have seen in the wild is the program doing a real, valid integer overflow check and simply warning you that the image might be too big. After that, it will happily carry on and allow someone to read your box. So what we see in our formula is that we have two extra clauses. Well, one extra clause, and it's going to conflict with our bug query, and that's not going to be satisfiable. You cannot not trigger the overflow warning and trigger the overflow at the same time. And keep in mind that because we're using concolic execution, the input that we give to this program is going to be a valid one. It's not actually going to be, if we were an invalid one and actually triggered that warning, we wouldn't have any problem, because we wouldn't even be testing the program, because we would say, oh, well, we found this image that actually causes the program to crash, right? Or at least have heap data corrupted on it inside. So why would you need symbolic execution or any other testing to help you out? You're done. I mean, well, you're not done with making it into an exploit or performing some other massaging it how you want to, but you're a good portion of the way there. So this constraint right here, the type of constraint that we're going to call it is a blocker constraint. So what do blocker constraints do? They're a name for constraints that you're going to have to deal with inside of your execution engine, so that either you don't generate a bunch of tests that aren't actually going to cause the program any problems, or another thing that blocker constraints can do is prevent you from using a path to a vulnerable code site to actually trigger the bug. The idea is that there are just one or so of these blocker constraints, or just a few inside of your path constraint, and the path constraint is mostly good, except for those. So some examples of blocker constraints are anything that really looks at the size of looks at the actual value of a user-controlled input, or of a tainted variable. So if we supply a tainted size to memcopy, it's going to do a check to see whether it can use one iteration of a byte move instruction to copy a single byte from one memory destination to another. So this is just an optimization, right? It's using assembly instructions that are geared towards performing this certain size operation fast. So what we're going, for example, from this optimized memcopy, we would have a constraint that says, well, your memcopy is going to have the lowest bit on it flipped. And if you actually go into a loop, which more generically you can look at with this example, where we're allocating a row or allocating a column for every row, a row for every. Wow, sorry, my brain, my brain's a little bit fried from the East Coast to West Coast time shift. So basically, you're allocating memory for every row of an image, right? So when you perform this loop, what constraints you'll generate, or what constraints will be met by the program, is 0 is less than your PNG's height. And then on the second loop iteration, you'll see 1 is less than than your PNG's height. So keep in mind that I is incrementing by 1 every single time this loop happens, and that's why we have different values on the left-hand side of the inequality. Eventually, when that loop terminates, we're also going to have a constraint that says, hey, the actual value, our actual height that was in the test image is not less than the actual height of the PNG. If you take all those constraints together, what that's going to tell you is, in effect, tell the solver is that your PNG's height cannot be changed at all. You're going to be stuck with the same height that your test file had. And that can certainly prevent you from causing an overflow if you have to make the other value large enough so that violates a check in order to cause the overflow. Another problem that you can run into, namely when you're trying to fuzz, if you're trying to implement generational search, which I'll come to in a bit, and you're trying to look at every branch that the program takes and generate test cases that make the branch flip in the other direction than what the program had originally taken, well, you might run into strlen and strcpy. And these are used in a lot of programs, and they will check whether any character of your string is null or not. So if you have a 500 character HTTP request that you look at, you're going to have 500 constraints that check whether or not each character inside of that string was equal to null. The only in this instance, I think what most of us would agree that the most valuable test case for this would be to have your symbolic engine violate the last check as opposed to any of the other ones. Why? Because if you change the last byte of the request to something not equal to null, you'll effectively increase the size of your string, which is probably what you actually wanted to do. But you'll still have to contend with the fact that there are going to be 499 other irrelevant constraints that you'll have to generate a new test input for and run the program again for each of them. Another really big problem that you can run into when you're using these symbolic engines are checksums. If your symbolic system is not aware of these, you can run into some ungodly constraints that you will not be able to solve fast. So CRC32, I think I've seen an instance of Z3 solving this within 10 minutes. Don't hold me to that because it's been 2 or 3 years since I saw this happen, but it takes a long time. You don't want to spend that much time on for every test case that you generate. And if you're dealing with a cryptographic checksum such as SHA-1, SHA-256, or even MD5, your solver might very well run out of memory before you're able to get any solution, let alone finish checking whether it's even possible to satisfy that formula. So what we want to do is we want to eliminate these blocker constraints from our path constraint, or avoid executing the code that constructs them. So if we eliminate the constraints, the idea is to take our path constraint and throw out all the constraints like the string copy, all that string copy stuff, the checksums, and the loop constraints, and the bogus integer overflow checks. The problem is that the naive way to do this is not feasible because we run into another problem whose best known solution is exponential in the size of the input. And the input in this case is the number of constraints. And remember, as I've said before and will say again, the number of constraints that you might have in your program is very large. Almost for example, on the 3 slides related to Klee, Diode, and Sage, with regards to the depth that of bug that they were able to reach in a program, virtually every one of those branches had to have a constraint associated with it. So we're talking either 35 constraints. So in that case, that's 2 to the 35th combinations that you might have to try for one of the most shallow bugs in that entire set of papers. So we can't do that. So we have to find another way. We could also try avoiding the blocker code. So the problem with this approach is that you might have to exercise the blocker code with the seed inputs that you have, because remember in the program that we have that's vulnerable to an integer overflow vulnerability. If we found any image that actually bypassed that check, we wouldn't be running this testing process. So the first strategy is called generational search, that has been come up with in literature relating to this topic. The intuition behind this, and this isn't exactly written down, but the idea is that you try to explore every path, or you try to create inputs that flip branches that are pretty near the path constraint. So the idea is that you flip one branch and you get all these you get a new test case that you'll create a bunch of other test cases with, and you'll effectively perform symbolic execution. You're pretty much reduced to performing symbolic execution on a lot of paths that will get you very, very near the vulnerable code block. So the idea is that you take a new path constraint, and for every branch, what you'll do is you'll negate it, and then satisfy every constraint up until that point. So you want to satisfy all of the branches that could lead to it, and then you're going to flip this one in the other direction and take another path through the program. So if we look at an example, the example of using this technique on our very simple test program, recall that this is the tree that we have for the pure symbolic strategy. So what generational search is actually going to do is, if we choose a test input that sets I equal to 3 and j equal to 100, we'll take a path through the program that makes the I equal to 3 branch flip to true, and the I plus j branch equal to it not flip to true, it'll flip to false, because 3 plus 100 is not equal to 31337. So what we'll first look at is the most deep branch that we found. And we'll say, well, I plus j is equal to 31337 was false before. Now we're going to make that true. And we need to meet all of the branches constraints above that. So we're going to set I is equal to 3 and j is equal to 31334, so that the sum of them is equal to 31337. So that'll be the first test case that we managed to generate for using a pure generational search. The second test case that we'll generate is we'll look at the branch on the first depth 1. We'll say, oh, I was equal to 3 on this one, on the first run. Well, what we're going to do is we're going to make an input that makes I not equal to 3. So an easy way to do that is keep j the same and set I equal to 4. So the problem with this is that if you don't add on certain optimizations to this, you can get very much caught up in creating test inputs like the ones that you saw for string copy. Now, another case that generational search will get caught up on is, wait for it. Okay, here we go. Imagine that u at max divided by I greater than j, that valid integer overflow check, is, let's say, 20 branches before that malloc. That's a large search space. That's to the 20 possible paths that you might have to exercise before you actually hit the vulnerable allocation site. You can get lost. So a technique that was created in response to this problem is called goal-directed search. So the idea behind this is to opportunistically include constraints that will help reach the target code block until you're able to get an input that actually triggers the bug. And you're told by some, as one author in the field calls it, Oracle tells you that your input actually did exercise the bug on a real execution of the program outside of the symbolic engine. Other optimizations to this include eliminating your loop condition constraints, which takes care of the first problem, and eliminating checksum constraints based on an annotated grammar. So we'll also get into an optimization that would help solve at least one of the problems that I mentioned if you applied it to generational search, and and in practice it actually is applied, but we'll go over why it doesn't actually completely save you. But to be fair, none of these techniques are going to save you, right? They can't save you for every program. So let's get into goal-directed search. So take our previous program and then send it an input, right? So we run it through our goal-directed search tool, and then we notice, here's a malloc with a tainted I and a tainted I times j, so let's get the expressions representing the transformations performed on those inputs to make them usable in this expression, and furthermore generate the bug query. Well, if you just send all that to the solver, you'll get out an assignment that definitely makes I and j greater than 1 million. That's not true for all solvers, but for the most part, you can assume that this is a very real risk. So what do? Well, you look at the path that the program took when fed this new input, and you note, well, the way that it differs from the path that it originally took was it took a path where I was actually greater than 1 million. So you include not I is greater than 1 million, not I is greater than 1 million. That should actually be I prime is less than or equal to 1 million, but we'll just ignore that. We'll include that in our path constraint. Then you might notice, we have j is greater than 1 million violated. So then we'll include that constraint. So now we have all three of these constraints in our solver, and what will happen is if you satisfy that first check and the overflow and the bug query, is that you'll get an input that crashes the program. It doesn't matter that you printed out warning the size is too big, because, well, you already crashed it, so why do you need to look any further? So here's an actual demo on a program. Here's an actual demo of this. So, oh boy, yeah. Just a sec, let me get the font large enough for the audience to see. Oh, Command Plus, thank you. I'm a new Mac user, so that's my excuse. Okay, so we have SymExec JPEG, and we set I and j equal to the values in the formula, and we notice that we can actually crash based on it. However, if we hadn't included the constraints for I and j, we would get a very large I and large j, and since Z3 is going to, actually Z3 is not running, but because of the format string we use to print those out, it's going to say that they're so large that they're above hex 08, and then was it like it's all zeros until you get the largest signed 32-bit integer. So we're actually able to bypass that using bypass that bogus check and trigger the overflow using goal-directed search. So we can also add enhancements on top of the techniques that we mentioned. We can do what's called constraint subsumption, which means that we're going to look at the constraints generated by every instruction, and then we're going to check if we visited the same instruction twice, whether the new constraint implies the old constraints. So, for example, if we go back to, if we just take a loop, what we'll basically see is that every one of the less than checks is implied by the less than check of the number one greater than the current iteration counter. So this technique will avoid depending on the metric that you use, so this will not actually take care of the problem that I described with the loop constraints, where you over-constrain your height to be a certain number, or even the string copy checks, for the reason that, well, each one of those uses a different variable, and you're still going to over-constrain. You're still going to over-constrain I in the first example. So another thing that you can add on top of these techniques is something called grammar assistance. You've probably seen this before, because if you've seen a parser before, you know what a grammar is, or at least you've used one. So what you can do with grammar assistance is take the seed input, push it through your parser, and look at the constraints and determine whether any of those are over string values. That's one example that you can do. You could say, oh, well, I noticed that this input is inside of the string and that it looks kind of like string copy that we're inside of. Well, what we can do is just exclude those constraints. Or what you can also do is exclude those constraints and then say, here is how big the string is. Let's use another fuzzing strategy for that portion of the program, which might get you a lot more mileage, because, well, you're not going to just be flipping everything to null. Of course, with some other character checks, it might be very good, because I think a technique like this actually could probably uncover breaking out of a current directory. If you have like a repeated dot slash pattern over and over again, you might be able to find that eventually, but it would be a pretty long process to do that, because you're going to have to solve all the other constraints in front of it, and then that one to get basically a dot, right, put in your input string. So so it might be better to just say, I know a good fuzzing strategy, let's apply it to this. So you can also use these file format parsers to tell, or to annotate them, and then say, this part of my file format is a checksum. I'm going to exclude any constraints that depend on this, and then recalculate the checksum and put it in the correct place before running the new test input. So the other thing that you can do with this is a technique that's used inside of American Fuzzy Lock. I'm sure some of you have heard of that utility. The idea is, and this can actually dramatically speed up concolic goal-directed search, etc., because it will, in effect, limit the number of times that you find the same bug twice with these tools. So the idea is that you try to get the minimum set of files that achieve the same code coverage as the union of the entire set of files, or test inputs that you have. And what American Fuzzy Lock does is it will trim your input based on knowledge that it has of the grammar. So instead of just cutting a file in half, for example, and using a technique called delta, a technique mentioned in delta debugging, where you keep you keep, say you have a really big file that triggers a vulnerability. Well, if you keep having the file, you might be able to find a smaller file that triggers the vulnerability but doesn't exercise as much code within the program. This will actually be a little bit more smart, so it might actually eliminate a string field and all of the size data surrounding it and size and type data surrounding it, for example, rather than just cleaving the program off midway through the type tag of the string, for example, if we're talking about fuzzing PNG. So an even more heavy-handed solution to dealing with this problem is something called selective execution. And the idea behind it is that you only fuzz the functions that you really want to target, and then take the inputs that the symbolic engine gives you and use those to recraft an input that is going to work on the real program. So if, for example, you're fuzzing, so the input reconstructor is called a test harness, and the driver is, the driver is their input reconstructor, and the test harness is the function that you're going to run, or actually going to fuzz. So the function that you write is actually going to call another function in your target program and bypass all of the checks that lead up to that, or all of the branches that lead up to that. So you can dramatically cut your search space down and use maybe use pure symbolic execution in a case where you might not have been able to otherwise. If it's a critical function in your program, say you're not doing this for offense, where you just need to find one bug, say you're trying to actually verify the correctness of a function. You could use this approach to target the one function that you want to verify the correctness of and know that you will exhaustively try out every single program path, and if there's a bug, and if there are no bugs, you're fine. Of course, there are caveats to this. If you have string data inside of there that is going to be processed with a loop, you can always grow the string. But if you have static data sizes, this technique could actually be very, very useful in a case like that. So in conclusion, symbolic execution is not exactly a simple technique. I actually have literally, let's see, about 44 more slides that I could go through on this topic, and they're all techniques that will dramatically speed up any attempt that you make to use symbolic fuzzing on a program. And that doesn't even get all of them, right? So the reason this is because programs are complicated, because they run on Turing machines. They can compute a lot of different functions. People are very creative, and they can encode a lot of different stuff in a program. So that pretty much necessitates the way that we search through them to have a lot of subtle nuances. So determine which of these techniques is right for you if you want to take any advice away from this talk, and try and see if they speed up your fuzzing process if you're using such an engine. With that, I conclude my talk. Thank you.